In this section of the course, we want to look at a mathematical operation called dimensional analysis. And dimensional analysis is essentially converting from one unit of measurement to another. So I want to take an example of this calculator, a calculator that I just happen to have in my office, and it has a known mass. I walked down the hall and I measured the mass of this calculator. So it's just a standard regular old calculator. It has a certain mass in grams. And it turns out that this calculator has a mass of 116.95 grams. So that's just the mass of the calculator that I just showed you. And maybe I would want to convert that mass, for whatever reason, to kilograms. So I want to know the mass of the calculator in kilograms. So we can use a process called dimensional analysis in order to solve this. And you may have learned before that you can simply just move the decimal place 3 times. And you would not be wrong. You could even make a strong argument that it's easier to just move the decimal place 3 times, and I'm just going to keep doing it that way. And again, you wouldn't be wrong. But there are many conversions, some of which you're going to see today, and many of which you will see throughout the chemistry course, where you can't simply move the decimal place. So I could not more strongly recommend that you spend some time learning the process of dimensional analysis. It will help you in chemistry. I actually use it in everyday life on occasion to convert from one unit to another. So dimensional analysis is very useful. Dimensional analysis always starts with an equality, something that relates one variable to another. And sometimes you have to use multiple equalities, as you'll see in further examples. But here we only need one equality because we know the equality between grams and kilograms. 1 kilogram is equal to 1,000 grams. So this is the equality. These two things are equal, and it relates the unit that we started with to the unit that we are trying to find. So if we start here with 116.95 grams times, we can write this equality as what is called a conversion factor. A conversion factor is simply one thing on the top and one thing on the bottom. So one of these will go on the top and one will go on the bottom. Well, what you can always do is think about the one that you want on the bottom. I have grams here, and I want grams to cancel out. So I put the 1,000 grams on the bottom. On top is the other one, 1 kilogram. And when you do that math, we simply multiply by the top, divide by the bottom. If there are multiple conversions, you would just repeat multiply by the top, divide by the bottom until you're done. We find out that there are 0.11695 kilograms is the mass of that calculator. So now we've converted the mass from grams to kilograms. Note that it's the same calculator, so it has to have the same mass. What has changed is the units. So this number of grams and this number of kilograms are exactly equal. Let's think about why. Well, we said that dimensional analysis always starts with an equality. So 1 kilogram equals 1,000 grams. Now we put one equal unit of measure over another equal unit of measure. Said another way, we have an equal magnitude divided by an equal magnitude, or this is 1. We then multiply this by 1. Again, it's 1 because you have one equal thing over another equal thing. This times 1 is itself. So the number has changed, right? This is 116.95 grams. This is 0.11695 kilograms. They're different numbers, but the magnitude is the same. Said another way, they're both express the mass of this calculator, just in different units. So these two things are exactly equal to each other. Let's take another example. Before we do, though, I do want to mention something about sig figs. Since we went from the metric system to the metric system, this is not a measurement. This is a defined equality. So the number of sig figs in my answer should match the number of sig figs in my starting measurement. I used a 2 decimal place balance when I measured the mass. So these do not have significant figures in them. And we'll contrast that to another example in a second where we convert this to an English unit, which is pounds. Let's say we use the same calculator, 116.95 grams, and we want to know the weight of this calculator in pounds. So we want to convert from grams to pounds. We need an equality. 1 pound is equal to 453.60 grams. This is not a defined equality. This is actually a measurement. We could take something of known standard of a pound and measure its mass in grams, and this is what we would find. I should note this is known with more decimal places. I just made it match 5 sig figs, so that our answer could have 5 significant figures. So I now have an equality, just like in the first case, starting with 116.95 grams times. I need to put one part of my equality on the bottom and one part of my equality on the top. Well, how do I decide what to put on the bottom? I decide what to put on the bottom based on getting the unit to cancel out. So in this case, I want grams to cancel out. So I put the 453.60 grams on the bottom. And on top, I put the 1 pound. Multiply by the top, divide by the bottom, and I find that the weight, if you will, of this calculator is 0.25783 pounds. Note, it is again the exact same calculator. So whether I express its mass in grams, kilograms, or pounds, all three of these things are equal because they're the mass of the calculator, or the weight technically of its pounds. They are not something different. So in order to do dimensional analysis, we're simply converting from one unit to another, but the magnitude of the unit are the same. Said another way, 116.95 grams is exactly equal to 0.25783 pounds, or 0.11695 kilograms. So that's what dimensional analysis is about. One other thing to quickly review. Dimensional analysis always starts with an equality, and then we can take that equality and we use it as a conversion factor, and we put the unit on the bottom that we want to cancel out. So in this case, grams cancel out, in this case, grams cancel out, and we're left with pounds, and here we were left with kilograms. So that's basically how this works. Let's look at another example. Let's say that we have 2,142 seconds, and we would like to know how many hours that is. In the previous cases, we had direct equalities between one unit and another. So we knew the equality between grams and kilograms. We knew the equality between grams and pounds. Let's assume for a second we don't know how many seconds are in an hour. You may know how many seconds are in an hour, but let's just assume we don't. So when we're doing a multi-step conversion, I suggest we do something called a plan of attack. And in this case, the plan of attack is to convert from seconds to something we know the direct conversion to, minutes, and then convert to hours. Again, you could do this in one step. It would not be wrong to do it in one step. Just for demonstration purposes here, I'm going to do it in 2 steps. So if we have 2 steps, we need 2 equalities. Well, we all know that there's 60 seconds in 1 minute. And we all know that there's 60 minutes in 1 hour. So let's start with our 2,142 seconds times. To go from seconds to minutes, we need to get rid of seconds. So we want to put the 60 seconds on the bottom. What's left? The 1 minute that we want to put on the top. For the next conversion, we now have minutes. So you always have whatever is at the top of the previous conversion factor. So in this case, seconds have canceled out, and we're left with minutes. So now we want to convert to hours. We need to put minutes here. We need to put the 60 minutes on the bottom and the 1 hour on the top. And again, these are exact equalities. So this is an exact number. It's not a measurement. It's just a definition. 1 minute equals 60 seconds. So said another way, this is 4 sig figs. So our answer should be 4 sig figs. And we get 0.5950 hours. Multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. Again with units, we notice we have seconds on the top, cancels out with seconds on the bottom, minutes on the top, cancels out with minutes on the bottom, and we are left with hours. So that worked out. Let's look at another example. I'm just going to move this up a little bit. Let's look at a more complex unit. In this case, we could have a more complex unit like 25.0 miles per hour. And we want to know what is that in meters per second. So our goal is to figure out how many meters per second that miles per hour is. And I'm just going to move this up a little bit more so I have a little bit more space in order to do this. So we have to go after one or the other first. So let's assume that we know how many meters are in a mile. So let's go for miles per hour and convert it to meters per hour. And if I know how many miles are in a meter or how many meters are in a mile, then I can do this if I know an equality between these two things. Notice that I went after one unit first and I ignored the other unit. Now we have hours. I'm going to go ahead and again assume that we don't know how many seconds are in an hour. So instead of meters per hour, I want to convert it to meters per minute. And then finally from meters per minute, I want to convert it to meters per second. So you may not know this off the top of your head, but you could look it up. 1 mile is equal to 1,609 meters. So that's our equality to go from miles to meters. Hours to minutes we've already used and everybody knows. 1 hour equals 60 minutes. And then minutes to seconds, 1 minute equals 60 seconds. So notice I'm doing 3 conversions, miles per hour to meters per hour to meters per minute, and meters per minute to meters per second. So I have 3 equalities that will allow me to do this. Now I want to start with my 25.0 miles per hour times miles is on the top and I want to get rid of it. So I'm going to put the 1 mile on the bottom and on top the 1,609 meters times. For the next conversion, I now have meters per hour because miles have canceled out. But hours is still on the bottom. So I want to get rid of hours, this time on the bottom. So I want to put 1 hour on the top and 60 minutes on the bottom. Now hours will cancel and I'll have meters per minute. I now want to get rid of minutes on the bottom. So I put the 1 minute on top and the 60 seconds on the bottom. When you do the math, you find out that this is 11.2 meters per second. Mathematically, to solve this, we multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. Note that if it's 1, you don't actually need to punch that into your calculator, but we just repeat, multiply by the top, divide by the bottom, all the way through until we get the answer. Another way you could do this is multiply all the tops and then divide by the bottom one at a time. Mathematically, that is exactly the same thing. Let's make sure our units cancel out. We have miles on the top, which cancels out with miles on the bottom. We have hours on the bottom, which cancels out with hours on the top. We have minutes on the top, which cancels out with minutes on the bottom. What are we left with? Meters on the top, seconds on the bottom, meters per second. Dimensional analysis is extremely useful. Note that way back in the first example, we could have moved the decimal place. This, you can't do by simply moving the decimal place. And although we won't actually use this particular equation in the chemistry course, this general idea is extremely useful. I would like to go over another example. So I just flip my paper over here of a different type of compound unit. Let's look at 0.0052 meters cubed. And I want to know how many cc's or centimeters cubed is this number of meters cubed. Chances are we don't know the relationship between meters cubed and centimeters cubed, but that's okay because we know the relationship between meters and centimeters. So let's start with that. 1 meter equals 100 centimeters. We know this relationship. Well, if we want to know the relationship of the cube of the unit, all we need to do is simply cube both sides. So, cube this, and what you get is 1 meter cubed equals 100 cubed, which is a million, or 1 times 10 to the 6, centimeters cubed. So 1 meter cubed is a million centimeters cubed, which we found from 1 meter equals 100 centimeters. Starting with 0.052 meters cubed times, we have a direct equality, so I didn't do a plan of attack, so we put our 1 meter cubed on the bottom, our 1 times 10 to the 6 centimeters cubed on the top, multiply by the top, divide by the bottom, and in scientific notation you get 5.2 times 10 to the 3, or 5,200 centimeters cubed as our answer. So these are just some examples of dimensional analysis, and this takes practice, and it's really important to practice this, practicing with plan of attacks and practicing with which one goes on the bottom, which one goes on the top, how to mathematically solve this by multiply by the top, divide by the bottom. It takes practice, so it's really important to practice this. I do want to go over 2 different things to finish this up, not that they're quick. I want to go over units as equalities, and I also want to do 3 real-world examples of how we might be able to use dimensional analysis to solve somewhat made up, but real-world type problems. So units as equalities. So one thing is someone make $15 per hour. How could we write this as an equality that we could use in dimensional analysis? Well, this would be $15 equals 1 hour of this person's time. So if they work 2 hours, they'll make $30. You could use this as a unit for dimensional analysis. What about density? Let's say something has a density of 0.623 grams per milliliter. This means that 0.623 grams of this substance equals 1 milliliter of this substance. So again, a compound unit that we change into an equality. Another one, let's say that someone is traveling at 57.4 miles per hour. This means that they will move 57.4 miles, and that will take them exactly 1 hour. So if something's per something else, it means it's per 1 of that something else. So this will become useful as we start to take a look at a few different examples of word problems that involve dimensional analysis. So let's take a look at those now. So the first one I have is, a student lives 125 miles from college. If it is mostly highway driving and the student averages 68.7 miles per hour, how many minutes will it take the student to get home? So we have how far the person lives from college, and we have how fast they're going. This question assumes that we know how many minutes are in an hour. which we've used before, plus it's pretty much common knowledge. So let's look at our plan of attack. We're going to start with miles, the distance the student is from their house. We're going to convert that to hours, because we know how long in hours it will take them to go that far. And then we're going to further convert that to minutes. So this is our plan of attack. It's basically a two-step conversion. So we need an equality. Well, if this person is going 68.7 miles per hour on average, that means that 68.7 miles equals 1 hour of this person's time. And the relationship between hours and minutes we've used several times before, and we know 1 hour equals 60 minutes. So now we have our two equalities that we can turn into conversion factors. So starting with 125 miles times, what do we want on the bottom? We want to convert from miles to hours. We want miles to cancel out. So we put the 68.7 miles on the bottom and 1 hour on the top. Times. For the next conversion, we want to convert from hours to minutes. So we want to get rid of hours, so we put the 1 hour on the bottom. We put the 60 minutes on the top. And if you look here at our essentially our dimensional analysis, miles cancels top and bottom, hours top, hours bottom, it cancels, and we end up with minutes. So this is what we want to do. At this point, it would be a good idea maybe to pause the video and make sure that you can mathematically solve this problem. And when you do, what you find is that this is 109 minutes of travel for this particular student. Let's look at the next one. The next one says, a student wants to purchase his significant other a 10-gram gold ring for her birthday. He gets a job making $12.75 per hour and has no other living expenses. I shouldn't say expensive, it should say expenses. If gold costs $1,252 per ounce and his uncle can make the ring for free, how long, in hours, will the student need to work to afford the gold in the ring? So this is a very lucky student. Okay, all he needs is the money for the gold, and someone will make the ring for him, and he doesn't have to pay rent or anything, or for food. So he's a lucky student. But anyway, it's basically a made-up problem to get practice doing dimensional analysis. So let's look at how we're going to do this. And one of the most difficult things that you're going to find both in these types of problems and in the chemistry problems is where do you start? And it turns out that the best way to do this is, unfortunately, to practice. So the best way to start this particular problem is with grams of gold. We know how many grams of gold this person ultimately wants to afford. And what we need to convert that to is time, how many hours this student has to work. But we don't know the cost of gold per gram. We only know it per ounce. And in the problem, we're given the equality between ounces and grams. So we want to convert from grams of gold to ounces of gold. After we convert to ounces of gold, we can then convert to dollars, the amount of money that this will take. And then finally, we can convert from dollars to hours because we know how many dollars this person makes in an hour. So the first equality is arguably the most straightforward because we have it. 1 ounce equals 28.35 grams. So 1 ounce equals 28.35 grams. Note that these are different systems, so this is technically a measured number. Now we want to go from ounces of gold to dollars. Well, we know that gold costs $1,252 per ounce. So $1,252 equals 1 ounce. When it comes to money and significant figures, I don't really know what the rules are, so I don't really want to get into that, and we're not going to really worry about significant figures here. Whether money is a counted thing or a measurement, to me it seems like it would depend on the case, but I'm not 100% sure. So we're not going to worry about sig figs. We're just going to answer this, the three significant figures at the end of the day. Now we have dollars to hours. So $12.75 equals 1 hour of this person's time, because he gets $12.75 for every 1 hour that he works. Now, let's start with our 10 grams of gold. So if we start with 10 grams gold times, we want grams to cancel out, so we're going to put the 28.35 grams. I'm just going to write gold here so that it's clear, per 1 ounce of gold. So we know what it's ounces of or grams of, but it doesn't matter. The equality is the same. So now grams of gold will cancel out. Times. For our next one, we want to get rid of ounces of gold. Well, 1 ounce of gold costs $1,252. So for the second conversion, we use the second equality. We put ounces on the bottom, we put dollars on the top. Now ounces will cancel out. Now let's look at the last one. For the last one, we want to go from dollars to hours. So we want to get rid of dollars, so we need to put it on the bottom, $12.75. And on top, the 1 hour of this person's time. Again, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. If you want to pause the video and make sure you get the right answer, that would be great. And when you do the math, you get 34.6 hours of time that this student has to work. You will never solve a question like this in a chemistry class. I mean, other than the fact that you're watching me do it right now in a chemistry class, but this isn't a chemistry question, of course. This methodology of using dimensional analysis you will use repeatedly in a chemistry course, and doing this and learning how to do this will really help you. Very quickly, I want to just go through and make sure my units cancel out. Grams of gold on the top, grams of gold on the bottom. Ounces of gold on the top, ounces of gold on the bottom. Dollars on the top, dollars on the bottom. I end up with hours, which is the unit that I wanted to finish with. Alright, last one, and then the video will be over. It says, according to Forbes magazine, it takes 9.5 watt hours to charge an iPhone from no charge to a full charge. And according to the EPA, a gallon of gasoline generates about 33,700 watt hours of electricity. Assume someone charges their iPhone once a day, and the 33,700 watt hours already takes into account the loss of energy when converting from one form of energy to another. How many years can an iPhone be charged on a tank, 15 gallons of gasoline? So these numbers are real. Now, this is a big assumption, okay, that you won't lose any energy when you convert from one form of energy to another, because you will. But otherwise, these numbers are real. So what you're going to find out is gasoline is extremely energy dense, and that shouldn't come as a surprise to you, because we use it to move things that weigh 1.5 tons, the average car, down the road at 70 miles an hour, right? So you need something that's very energy dense, because that takes a lot of energy to do. So let's take a look at how we're going to solve this, starting with our plan of attack. Remember that with practice you'll start to see where to start. At first, what can be one of the hardest things is figuring out where to start. Here, we want to start with gallons. And we want to convert from gallons of gasoline to watt hours of electricity. Once we have watt hours of electricity, we want to see how many times we can charge the phone. Charges, we then want to convert to a unit of time, which is days. And then finally, we want to convert from days to years. And we're going to assume that it's not a leap year, so 365 days in a year. You could use 365.25 if you wanted to take into account leap years, but I'm not going to bother with that. All right, so we need a relationship between gallons and watt hours. Well, a gallon of gasoline generates about 33,700 watt hours of electricity. So, 33,700 watt hours equals 1 gallon. Now, we need to know how many watt hours it takes to charge our iPhone. Well, according to Forbes magazine, 9.5 watt hours equals 1 charge of the iPhone. Now we want to know charges to days. How often is this person going to charge their iPhone? And it says they're going to charge their iPhone once a day. So 1 charge equals 1 day. And then finally, days to years, and we already mentioned we're going to use 365 days equals 1 year. So, starting with 15 gallons of gasoline times. Our first equality is 33,700 watt hours per gallon. We want to put the 1 gallon on the bottom. 33,700 watt hours on top. Gallons will cancel. Times. Now we want to go from watt hours to charges. We want to get rid of watt hours, so we put the 9.5 watt hours on the bottom, 1 charge on the top. Times. We want to convert from charges to days. We want charges, or charge, to go away. So we put the 1 charge on the bottom and the 1 day on the top. Finally, we want to convert from days to years. So we put 365 days on the bottom and 1 year on the top. Let's make sure that it works. We have gallons on the top, gallons on the bottom. Watt hours on the top, watt hours on the bottom. Charges on the top, charges on the bottom. Days on the top, days on the bottom. We're going to end up with years. When you do this and you round to 2 significant figures, you will find that it is 150 years. And again, these are not made up numbers. Theoretically, there's enough energy in 15 gallons of gas to charge an iPhone once a day for about 150 years. Dimensional analysis, again, is a concept that we use regularly in chemistry. It is definitely worth your time to practice with dimensional analysis.